Hi, I'm Claudio Argentino and I'm a postdoc fellow at CAGE-UiT. My research interests lie within the field of marine geochemistry, with particular emphasis on hydrocarbon seepage environments. My current research project aims to reconstruct the dynamic and history of past methane emission in a specific area located in the southwestern Barents Sea. In order to do that, I study the composition of pore water, gas in the sediment, and the geochemistry of a sediment. Within the ACMA project, I will take responsibility for pore water and gas sampling.
In the project ACMA, we will investigate also the history of methane emission in the Arctic. And we do so because we would like to understand if the methane emissions in the Arctic are related to climate change, the global warming. We know that the Arctic is warming much faster than other regions on the planet, and we would like to see, to understand, to measure if this warming is affecting or will affect methane releases from the Arctic marine realm. In order to do so, we start, by the way, investigating the history of methane emission. So which or how was the methane emission in the past? And Claudio is an expert in the reconstruction of methane emission in the past, and he studied that starting from a particular sample.
Yes.
Claudio, what is this?
So what's so special about this rock? It may look a normal rock. Well, indeed, it is a marine carbonate that is not very unique. What's so unique about it is the chemical composition and the origin of this rock. Well, it forms at hydrocarbon seepage environment when you have this huge amount of methane reaching the surface. And so you have this carbonate precipitation at the seafloor or close to the seafloor.
The sulfate-methane transition zone is an important redox boundary in marine sediments, and it is located at variable depth between the seafloor, mainly depending on the magnitude of the upward methane flux. The sulfate-methane transition zone is located at the intersection between the sulfate and methane concentration profiles. It is right there that consortia of microorganisms consuming methane and sulfate perform the biogeochemical process known as anaerobic oxidation of methane. As an end product of this reaction, bicarbonate and hydrogen sulfide are released into pore water, leading to the precipitation of methane-derived oxygenic carbonate and iron sulfides, such as pyrite, in the sediment.
I see something else here, Claudio, because I see some bivalves. What are those?
Yes, if you pay attention, you can see them. You can see some fossil shells.
Part of the hydrogen sulfide generated by the anaerobic oxidation of methane can escape precipitation in the sulfate-methane transition zone and diffuse toward the seafloor, where it sustains chemosynthetic communities which utilize sulfide as an energy source for their metabolic processes. Seep fauna lives on the seafloor or in the upper few centimeters of sediment, so with the proceeding of carbonate precipitation, and where the sulfate-methane transition zone lies close to the seafloor, this fauna might be trapped in the carbonate. This is the reason why we observed fossil shells within methane-derived carbonates.